close this. Okay, is that visible?
Yeah.
Okay, so I don't think I can see the chat while I'm presenting. So if somebody asks a question, if you just want to unmute and ask it, I'm happy for interruptions during the talk, so people can ask questions whenever. Yeah, so I'm going to talk about compositional reasoning with process theories, and the less serious title for this talk is how to send encrypted data or teleport particles using one weird trick. So I'm going to go through this example. If you notice that some of these slides are a bit silly or have some memes in, it's because some of these slides came from a talk that I gave for high schoolers, which you can find on YouTube. I gave some 6 months ago or so. So yeah, let me get into it then. Okay, so a lot of the background for this is a book called Picturing Quantum Processes that Samir mentioned. And the idea of this book, and more broadly this research program, is to teach quantum theory using a kind of a diagrammatic notation, and we call this diagrammatic reasoning. So in this kind of notation, the pictures really are the math. So they take the place of equations, and how you calculate is you draw a picture and then you transform this picture into another one and then another. And then at the end, you calculate the result of something this way. And what that something is in this book is it's calculating, for instance, what quantum theory tells us will happen if we run a certain experiment, something like that. Okay. Yeah, that's me. So I'm going to tell you what the one weird trick is. So I'm kind of giving away the punchline right here at the beginning. And the weird trick is string theory. But not string theory in the sense of complicated physics, but literally the theory of strings. Okay, and the most important thing about string theory is that if I have a bent piece of string like this, then if I just pull on it, it becomes a straight piece of string. Okay, so by the end of this talk, you'll see that this is the main trick behind both encryption, so sending secure messages, and also quantum teleportation. Okay, so here's a little warm up from the book, from Picturing Quantum Processes. So typical quantum systems, so the things that are studied in quantum theory are microscopic systems like photons and electrons, but it's not actually that important what specific kind of system you're talking about, because the basic rules of quantum theory are the same. No matter what type of system you're talking about. So as long as the system is subject to the rules of quantum theory, we don't really care what kind of particle it is. So in PQP, we actually use a hypothetical quantum system to explain a lot of things, and that quantum system is a dodo. So this is Dave, and Dave is the quantum dodo, which features throughout Picturing Quantum Processes. And the reason we use Dave really is that we can just put him in various places in the world and kind of explain different quantum phenomena. Okay, so the unique thing about Dave is his state. So what kind of state he's in is the same as the state of a qubit, and a qubit is the simplest kind of quantum system you can talk about. Okay, so what is a qubit? Well, it's a quantum bit. So what is a bit? Well, a bit is something that has a few important properties. So a bit has two different states that it can be in. So it's some bit of information, and those states are 0 and 1, or off and on. And an important thing is it can be updated in any way we like. Okay, so for instance, here's a way that I can update a bit. Like if it's 0, I can send it to 1, and if it's 1, I could send it to 0. Right. So another more mathematical way of saying this is I could apply any function I like to my bit to get a new bit. Right. So I could this one like flips a bit, but this is something that's also perfectly allowed for bits. I can send my bit 0 to 0, and I can send my bit 1 also to 0. So this is like I can just delete my bit and set it to 0. Okay, and they can also be read freely at any time, which if you don't think about things like quantum systems, just seems so obvious that you shouldn't even say it. If I have a bit written down on a sheet of paper, or if it's on the hard drive of my computer, I can just look at it any time I like, and that's no problem. So that becomes a problem if you start talking about quantum bits. So quantum bits are better than bits in one way, in that they admit an entire sphere of states. Okay, so the state of a quantum bit, you can visualize this as a point on the surface of a sphere. Okay, and the way you can think about this as being related to normal bits is maybe think of the North Pole as 0 and the South Pole as 1. Okay, but now we have all these other places in the sphere that a quantum bit could be in. But the kind of catch here is the only things that I can do to this sphere is I can just rotate the whole sphere. Okay, so I can take my sphere and I can turn it upside down. That's allowed, and what that will do is it'll send the North Pole to the South Pole and the South Pole to the North Pole. But there's no way that I can send the North Pole and the South Pole both to the North Pole. Right? That's not a legal way that I can take a ball and rotate it. I can't take two things that are at different places and put them at the same place. Okay, that's just not allowed. And the only way that you can access qubits, unlike bits where I could just look at them, the only thing I can do to access a qubit is to measure it. Okay, and this is a process which gives me some information, but in the process it destroys the state of the system. Okay, so I'll try to give a flavor of what quantum measurements are like. So here's a sphere. It's a very familiar one. I'll use as an analogy. And as I was saying, you can have the North Pole and the South Pole, and you can think of these as like 0 and 1 states of a quantum bit. But let's assume that the state of Dave is just some other point in this sphere. Okay, so we'd like to get some information about what state Dave is in. And the way we do this is by performing a measurement. Okay, so the rules of measurements, using this kind of language of being at places in the world, is we're allowed to ask Dave whether he lives at a specific location on Earth in the sphere or its opposite location. Dave will always answer correctly, right? And I put some sort of scare quotes around correct, meaning that as soon as Dave gives an answer, that answer will be correct. Okay, so in other words, as you'll see in a bit, it could be that once Dave gives an answer, his state will actually change to make his answer correct. Okay, so an example of a measurement is I could ask Dave, are you at one of two antipodal points? You know, are you in Zeeland in the Netherlands, or are you in New Zealand? These are basically across from each other exactly in the world. And in this case, Dave would say, well, I'm in Zeeland, because that's where he is, and that was the correct answer. Okay, and he'll always say that. If I keep asking him that, he'll always say that. But if I ask Dave, are you at the North Pole or the South Pole? Those are the only answers he's allowed to give. So he might say, I'm at the South Pole, and then if he says that, then his state will immediately be at the South Pole. Or if he says he's at the North Pole, his state will immediately jump to the North Pole. And this is something that happens probabilistically in quantum theory. So there's some probability that he'll jump to the North Pole and some probability he'll jump to the South Pole. But the point is, after this happens, we can no longer remember where he was in the first place. So it kind of destroys the state of the system. Okay, and there's Dave getting chased by a polar bear. Okay, so that was just to give a kind of a flavor of what quantum theory looks like. Getting sort of toward the math of quantum theory, or various other things that can be formulated in a way like quantum theory can. We introduced this notion of process theories. Okay, so a process theory is made up of processes. Okay, and a process is just anything that has some inputs and some outputs. Okay, so we think about having some inputs. In physics, we would call these systems. You know, I could have a few particles, and then something happens to those particles. You know, maybe they interact with each other, and then we get some outputs. You know, some different particles or particles in a different state. But really, a generic process is just anything we can describe in these terms. So as something which has some inputs, then something happens and it produces some outputs. Okay, so a mathematical process could be something just like a function. Okay, so these are like the kinds of things that you'd meet in high school math. You know, I have this function f, which takes in two numbers and it gives me another number. Okay, and the way it does it here is it takes this first number and maybe it squares it, and then it adds this second number, and that gives me a result. Okay, that's a kind of process. It's an abstract mathematical process. It's not something that exists in the world, but it takes some inputs to some outputs. So for example, if I plug a 5 and a 1 into the bottom of this process, well, 5 squared is 25 plus 1, then a 26 should pop out the top of this process. Okay, so I can think of this f as kind of like a little machine which is turning its inputs into some outputs. And importantly, process theories always include one special process, which is the do-nothing process. Okay, and in the case of functions, that's just the process which takes a number and it gives me that number back. So f of x equals x. So here I just draw this as a piece of wire. And if I plug, say, 5 into the bottom of this wire, then 5 should come back out. Okay, so that's a perfectly good process. But like I said, processes can be anything, not just mathematical things. So here's one from computer science. This is a computer program which takes in a list and it returns a sorted list. Okay, using something called a quicksort. Here's a thing that you could find in the world. Binoculars take in sort of light in 2 of their holes, and they put out sort of magnified light in 2 of their holes. There's a cooking process which processes eggs and bacon into breakfast, and here's a baby process which turns food and love into noise and poo. So this one I came up with when I was writing the book with Bob, and his daughter Marika was born in the meantime. So it's more a joke for him. So not all processes make sense to plug together, right? So for instance, it doesn't make any sense to plug the baby process into a computer program. But a family of processes which do make sense to plug together is called a process theory. Okay, so when I say a process theory, I'm sort of fixing a context of things, like a universe of things that I'm talking about. Okay, so an example of a process theory will be the theory of quantum processes. And then that means that we're really talking about quantum theory. Okay, so some examples of process theories are, for instance, functions. You could have a process theory of logic where I've got sort of assumptions coming into the bottom of my process, and I have conclusions coming out the top. Electrical circuits where maybe I really have some voltages and currents sort of coming in and through these wires, something like that. And maybe a resistor is a process. Computer programs, maybe in some programming language. And as I said, quantum theory is an example of one of these process theories. Okay, but it's a very general thing. The point is not to make too many assumptions about what kind of theory we're working with, just that we can describe it in these terms of inputs and outputs, and I can really start drawing these things as boxes and plugging them together to make more interesting processes. Okay, so to make this even a bit more concrete, I'm going to introduce another kind of mathematical process theory using some, well, depending on where you went to high school, just using some high school mathematics to define this thing. Maybe even some middle school mathematics if you went to middle school in Germany or something. So I'm going to talk about the process theory of relations. So what is a relation? It's like an unreliable function. Okay, it's a function is something which takes an input and it gives me one output. A relation, it takes an input and it can give me possibly many outputs. Okay, so an example of a relation is a function. So here's a function, the not function or the not gate. Okay, it takes as input a bit. So if it takes in bit 0, it gives me bit 1. If it takes in bit 1, it gives me bit 0. Okay, so that's a function. It's also a relation. Okay, so it relates everything in this first blob to something in this other blob. But here's another thing which is a bit like a not gate. I call it the not-ish gate. Okay, and this thing, if it takes in a 0, it gives me a 1. But if it takes in a 1, it either gives me a 0 or it gives me a 1. Okay, so this is like maybe I have something which does what a not gate does, but sometimes it fails and just doesn't do anything at all. Okay, that's maybe one way I could, some kind of machine I could model with such a relation. Okay, and I can draw it in this kind of blob picture here where I see that 0 is related to 1 and 1 is related to 0 or 1. Okay, so I could interpret this as, well, I'm not exactly sure what will happen if I plug in 1 into this thing. It could either go to 0 or to 1. Computer scientists will often say that something non-deterministic happens here. So we can't decide in advance what will happen. It could be either of those things that happen. Okay, and the way you can start, I mean, I can represent these things as boxes with wires, and the way that I start plugging these things together is really just by, you may have learned how to do this in school, basically by tracing the arrows through. Okay, so here's a set of 3 things and a set of 4 things, and here's a relation R, which relates, say, A1 to B2 and A2 to B3 and B4. And then here's a relation S, which relates B1 to C1, B2 to C1 and C2, B4 to C3. Okay, and now what do I get if I plug R into S? Okay, this is like I'm composing 2 relations. I get another relation. This relates A1 to C1 and C2. Okay, so how do I figure that out? Well, here's A1. I should just see all the places that I can get to from here. Okay, well, A1 goes to B2 and then it goes to C1. You can see A1 goes to C1 there. A1 goes to B2 and it goes to C2. So here's A1 goes to C2 there. A2 here, well, if it goes to B3, that's a dead end, so that doesn't go anywhere. But if it can go to B4 and then go to C3, so A2 goes to C3 here. And A3 doesn't go anywhere, so it doesn't go anywhere here. Okay, so that's how you can compose relations in this process theory that I'm defining. Okay, and I can also think about relations that have more wires. Okay, and this is really just relating lists of things to lists of things. Okay, so here's something with 3 bits as its input and 2 bits as its output. Okay, well, I can just draw this as a bigger thing. Here's all the possible ways that I could write down 3 bits. Okay, there's eight different combinations of 0 and 1 here. Okay, so that's all the lists of 3 bits there that exist. And then some relation is just mapping some list of 3 bits to a list of 2 bits. Okay, so this relation R could be this thing. Okay. And that's basically how this process theory works, and how at least at the low level, how you do some calculations with it. Okay, so here's kind of an interesting philosophical question. How many lists are there that which have 0 things in them? Well, you might initially want to say that there's 0 of those, but in fact there's exactly 1 of them, right? The empty list is a list with nothing in it. Okay, so no wires means the list of 0 things, which there's 1 of those. Okay, so I can write this maybe as just Here, I just put some parentheses with nothing inside. Okay. The reason I talked about that is I want to talk about these processes which have no wires into them. Okay, so we call these states. And the way you can think about this is this is a process which is taking some systems, some particles or something, and setting them just to some state. Okay, so you could think, well, I've got some memory on my computer. I have a bit or something. I set it to 0. Okay, that's a state. Okay, so for this example of bits, in this process theory of relations, here's some states. Okay, so I could call this state 0, and this relation is really just pointing at that element 0. Okay, so that's a relation from the empty list to 0. Okay, and this state 1 is just pointing to 1. Okay, and if these things had to be functions, these would be the only things that would be allowed, right? I have the only two states, like I was talking about before, of a bit are 0 and 1. But relations allow something else, which is this state, where I relate both to 0 and to 1. Okay, and what does that represent? Well, that represents the fact that I have a bit, but I don't know what it is. Okay, so I can use this relation to represent that I might not actually know what's going on with my bit. Okay, and that's quite useful when talking about things like cryptography, where you may or may not know things. Okay, so an interesting thing about states is that they can be separated. Okay, so here's an example of a state which is separated into two different boxes. Okay, and here, when I put this together into a relation, you can see that I'm relating to this part of the state is relating to the 0 here, and this part of the state is relating to the 1. Okay, and I've really given you, I've described this state by telling you something about the first system. That first bit is 0. And I've told you something about the second system. That second bit is 1. Okay, that's something that's separated. The knowledge of the whole system is exactly the knowledge of each of these component pieces. Okay, and here's one that's also separated. Okay, so here I've told you that the first bit is 0, but I don't know what the second bit is. Okay, so again, I've told you something about the first system, and I've told you something about the second system. Okay, there's something I don't know here. I'm not sure exactly if I have 0, 0 or 0, 1 in my pair of bits, but I certainly know that my first bit is 0. But states can also be correlated. Okay, so I mean, if you've done statistics, you should be familiar with correlations. This idea where I have some unknown which I could represent with some probabilities or something, and things can be correlated to each other. Okay, so this state, say I have 2 bits. I don't know what either of those bits are, but I know that they're the same. Okay, so those 2 bits are equal. So there's 2 possibilities. Either I have 0, 0, or I have 1, 1. Okay, well, that's a state of knowledge about 2 bits, which doesn't separate into 2 pieces. Okay, it's something that's spread across both. So knowing that these things are the same doesn't mean that I know something about my first bit and I separately know something about my second bit. I know something about their relationship. Okay, and that's very important that we can have these kinds of correlated states. And this is such an important one that we usually draw it as a piece of wire that's sort of bent around like this. Okay, so you can start to see how we're working toward having this zigzag piece of string. Okay, so I can turn this whole thing upside down, and I can also talk about these things called effects. Okay, so a state is maybe seems at least somewhat familiar. An effect might seem like a bit of a strange concept, but really this is just a process which has some inputs and no outputs. Okay, and conceptually we think about these things as answers to a question. Okay, so for bits, there's really only 2 questions that we could ask. Okay, one of the questions is, what is my bit? Okay, and that really has 2 answers. my bit is 0, okay, and I'll represent it by this effect, mapping the 0 to the empty list here, or my bit is 1, mapping the 1 there. Okay, so that's a question. And if I take my state, my 0 state, and I plug it into my 0 answer, I'll see that I'll get true. And if I plug it into my 1 answer, I'll see that I get false. So that's why sort of these questions and answers fit together. There's also a kind of a trivial question, which doesn't really ask anything. It just says, do I have a bit here? And it will just give me the unique answer, which is, there's a bit here. Okay, so anyway, that's a less interesting kind of effect. Okay, so sets of effects together form measurements. Okay, so a measurement is really just asking a question here and getting one of those answers. Like, what is the value of my bit? I could get 2 answers. I could get 0. I could get 1. And yeah, so there's 2 possible measurements for 1 bit. This conclusive measurement, which is just reading off the value of the bit, and I'll get an answer 0 or 1. And there's this inconclusive or sort of trivial measurement where I actually don't learn anything. Okay. For 2 bits, things get more interesting. There's a lot more questions I could ask about 2 bits than 1 bit, or even asking about each bit individually. So like states, we could have separated measurements. Okay, we could ask, well, what is the value of my first bit? What is the value of my second bit? That has 4 answers, right? So corresponding to each of the 4 possibilities that could happen. Or I could have correlated measurements. So 2 bits, and I could just ask, are these 2 bits equal to each other? Okay, and that has 2 answers. That has yes or no. Okay, and I can represent each of these by an effect. Okay, so that's like an answer that I get when I ask the question. And I can draw that this way. So I can draw equal as just the cut upside down. Okay, and if you look at the relation, it's actually just that twin state sort of flipped around. Not equal is I just take one of my bits and I flip it, and then I ask if those 2 are equal. Okay. So that's how I can represent not equal. So this is just a bit of a slightly more mathematical way I can write these 2 possible outcomes. Okay, so let's do some string theory now. Let's compute this zigzag shape. Okay, so I told you that this is a process. This is the twin state, and this is a process. That's the equal effect. These are the do nothing processes. So I should be able to plug these things together and actually compute what it equals. Okay, what that is, using the rules of composing relations. Okay, so let's do that. So here's my twin state. And that's something from no bits to 2 bits. Okay, if I put the do nothing, if I put the identity process next to it, then that's something from 1 bit to 3 bits. Okay, and what does it do? Well, it takes that first bit to itself. You see, 0 has gone to 0 there, 0 has gone to 0 there, 1's gone to 1, 1's gone to 1. And then it's put the twin state next to it. Okay, so here next to that 0 there, I could either have 0, 0 or 1, 1. Next to that 1, I could also either have 0, 0 or 1, 1. Okay, so if I put in a 0, I'll get a 0 with a twin state. And if I put in a 1, I'll get a 1 with a twin state. Okay, so that's what this whole relation is. And then I can do the similar thing upside down. Okay, so here I've got the equals of the twin effect, and I put it next to the do nothing process. And this is the relation that I would get when I compose these things side by side. Okay, so now I look at what happens when I trace these paths. Right, 0 goes to 0, or it goes here and it hits a dead end. Okay, so 0 relates to 0. Here 1 either goes here and hits a dead end, or it goes to 1. So you can see that 0 goes to 0 and 1 goes to 1. Okay, and that's the do nothing process. That's the identity process. Okay, so what I calculated really was just this equation. Okay, I just gave you the rules of putting these relations together, and then I did a calculation one time. So I have to do this one time, and now I know that this equation between pictures is true. I never have to do that calculation again. From now on, I'm just going to use this equation to prove things about pictures. Okay, so at some point, I'm not going to be looking at the blobs anymore. I'm really just going to be using these picture equations to do anything that I want. Okay, and this is the equation, which is the man sort of pulling the piece of string straight. Okay, but I said this had something to do with cryptography. So I can tell you now what this has to do with cryptography. Okay, so if you've never met crypto before, which I would assume many people have not, here's the simplest way that you can do encryption. Okay, so encryption is basically a way that I can use a secret key to encode a message in such a way that if somebody's looking, they won't be able to read that message. Okay, so suppose me and Bob each have an envelope with the same random bits sealed inside. Okay, this is called the key. Okay, this is our encryption key. This is a shared secret bit we have, which we're going to use to send a message. Okay, so I want to send a secret bit to Bob. Okay, I want to tell him something, but I don't want anyone else to know what I told him. Okay, so what do? I open my envelope, and I tell Bob if the bit inside the envelope is the same as my secret bit. Okay, so I look at these two bits and I say, are they equal or not equal? And what do? I tell him the answer to that question. Are they equal or not equal? Okay, so Bob opens his envelope. And if I told him that they were equal to each other, if they were equal to each other, then Bob knows what my bit is, right? Because my bit equals the bit in the envelope, which equals the bit in Bob's envelope. Okay, so he has it. He got my bit. Otherwise, Bob just takes the other answer. Okay, if I looked at my bit and saw that it was different from the one in the envelope, then Bob should just look at the one that's in his envelope and flip it. Okay, and then in either case, he'll get my bit. But the only thing the rest of the world knows is whether that bit in the envelope was the same as my bit. And that really had nothing to do with the value of my bit in the first place. Okay, so if you don't know what's in the envelope, then you don't know what my bit is. Okay, so that's what it was in words, and you can kind of read that and reason out that yes, that works. Okay, that's called one-time pad cryptography. So it's kind of the first cryptographic protocol they teach you in a security class. Let's do this with pictures. Okay, so first of all, the shared bits in the envelope we can represent using this twin state. Okay, so we don't know what bits are in the envelope, and it doesn't matter what bits are in the envelope. It just matters that they're the same as each other. Okay, so that's the twin state. And here's where I'm comparing the bit that I have to the bit in the envelope. Okay, so I'm just looking at those two bits and I'm judging whether they're the same or not the same. Okay, that's a question which has two answers, equal or not equal, right? And that's represented by these two effects. Okay, and here's how I put that whole thing together. Okay, so what do? I have this secret bit here, and Bob and I also share bits in these two envelopes. Okay, now I do a measurement. Okay, so it's a bit strange to call this a measurement, right? But I just ask a question of these two bits: are they equal or not equal? And depending on my answer, this question mark here will either be do nothing, the identity, or it will be not. Okay. And what Bob needs to do is just do the same thing as what's in this box. Okay. So a bit more concretely, there's two cases, right? The bits are the same, in which case I fill in just a wire for that question mark, and Bob doesn't need to do anything. And you can see that Bob gets my bit, okay? Because I just take this piece of wire and I yank it straight. Like that. Okay. So in that case, Bob gets my secret bit. The other case is that the bits are different. So I got this outcome, which is really saying that these two bits are not equal. Okay, so I tell Bob the bits were not equal. Okay, that's all he needs to know, because once he knows that, he knows he should flip the bit that was in his envelope. Okay, now let's see what happens. Well, if I yank the wire like that, well, now I have a not and then a not. Okay, and that's a double negative, right? So not is the same as doing nothing. So those cancel out, and he gets my bit. Okay, so this works in both cases. So I have a technique for sending secret bits, which always works, as long as I have these shared bits in the envelope. Okay, and that's how one-time pad cryptography works. So while that may have seemed like maybe a slightly more complicated way of explaining it than that page full of words, the thing that you win here is that you can now just change the process theory, and you can see instances of this trick happening everywhere. So in particular, quantum teleportation works exactly like that, but in a different process theory. Okay, so if you understood this thing about the bits in the envelope, then you basically understand already how quantum teleportation works. Okay, so you might not know the underlying math of quantum theory, but you know the trick. You know the trick that gets used to make this thing called quantum teleportation work. Okay, and what is quantum teleportation? It's a way of using entanglement to send particles over large distances. So it's quite a bit more mysterious thing than sort of bits and envelopes and secret messages and so on. Okay, so in quantum theory, we realized the twin state using this thing called quantum entanglement, which is a concept coming from quantum theory, but it's really represented related things is a certain entangled state called a Bell state. And that's named after John Stuart Bell, a famous physicist. And the analogous thing to looking at my two bits and saying, are they equal or are they not equal? Well, I have that kind of measurement. It's a quantum measurement, but actually rather than having just two answers, it has four answers. Okay, and the reason for that is that a qubit is a sphere, and there's several different ways that I can do a knot on a sphere. Okay, there's several different ways that I can flip a sphere 180 degrees. So in fact, what you can see is that I can do a measurement with three different quantum knots. Okay, so there's knot 1, knot 2, and knot 3. And what these correspond to are actually just flipping the sphere. Okay, so here's one kind of knot gate where I just flip the sphere upside down. Right, so there's three different ways that I can do that. I can flip it on the x-axis, the y-axis, or the z-axis. Okay, so there's a very good reason why that's a good quantum measurement, and I need a little more time than I have today to explain why that's the case, but it is explained in the book. But it's totally analogous to this looking at a pair of bits and seeing whether I should put a wire there, or I should put a knot there. The only thing that's special about this quantum case is there's a few different knots that could go there. Okay, so I look at this protocol, right, this crypto protocol, and now I just make everything quantum. Okay, what did I do? Well, all I did was I took the thin wires and I made them fat wires. Okay, that just means that I changed from talking about relations to talking about quantum processes. Okay, but the reason this works is exactly the same. Okay, now I have a quantum state. Here, maybe I have a particle or something. I'll do a measurement. I'll get one of these four outcomes, and I'll tell Bob what outcome I got. 0, 1, 2, 3, or something like that. 1, 2, 3, 4. Based on that, he'll know what kind of NOT gate he should do here, or if he should do nothing at all. Okay, and what happens is that our two quantum knot gates now, if I rotate by 180 degrees and I rotate by 180 degrees again, I've done nothing. So these things cancel out, and Bob gets my particle, no matter what my outcome was. Okay, and that's how quantum teleportation works. Okay, and this is well, it wasn't explained in pictures, but this is the quantum teleportation protocol that was introduced in the 90s, and the kinds of things that people are doing in all kinds of physics labs all over the world. And they've even managed to teleport particles to space and done quite interesting, pretty high tech stuff using this trick. And yeah, so that's a simple example of diagrammatic reasoning that really just relied on two kinds of rules. This rule that I can take a piece of wire and I can bend it straight, and also that this certain kind of box cancels out with itself. Okay, if you build up more of these rules, and in picturing quantum processes, we use diagrammatic reasoning and some more rules to build up a lot of other stuff. So you can talk about things like quantum cryptography, quantum algorithms, quantum compiling, the foundations of quantum theory. So why is the universe a fundamentally non-local thing? All of these things you can describe using diagrams and reasoning with diagrams. So it's actually a pretty rich language that gives you a handle on a lot of these things. I want to mention so I should say that we've been using this kind of technique to teach a master's course in Oxford, which I just figured out recently has been running for 10 years, which is now called Quantum Processes and Computation. So it's a 4th year in master's course. And there's a couple of sequels in the works. So there's one that's kind of, in terms of sophistication, it's a step up. So it's for graduate students who are interested in a career in quantum computing, or in academia around quantum computing, called Picturing Quantum Software, which I'm working on now with a former PhD student. And there's also a book that's aimed at high schoolers, which Bob and Stefano Goggioso are writing, have written. It's done now. It's in production, or in early stages of production, called Quantum in Pictures. And this book is the basis of an experiment that we're in the early days of, so somewhat in the formative days of. And particularly if people have comments about this, I'd be interested to hear them. So the main question that we're trying to answer is, can you use diagrammatic reasoning to teach quantum theory to kids? If you look at Bob Kuka's old paper, Kindergarten Quantum Mechanics, he claims that you can use these techniques to teach it to kindergartners. We thought we would be a little bit less ambitious and try to teach it to high school kids initially, before trying kindergartners. Yeah, so we want to see if this is possible. So the provisional format for this study is we'll take 100 to 150 high school volunteers, which we found or can find through various networks, taught in small groups online over the course of about 6 weeks, a kind of tutorial course. The main thing is that they have short YouTube videos to watch, and then they have online discussions with TAs or with sort of teachers in small groups. There's a written exam at the end. Well, I should say a drawn exam. So it's draw me a picture that solves this problem, basically. And then some surveys and interviews, or interviews before and after. So that's the kind of meat of the study. And some of the details we're in the process of fleshing out. And some things that are kind of challenging with this. Well, first of all, selection could be tricky, right? Because as I've said, we're finding these volunteers, so they kind of self-select. We're naturally going to get, I think, quite interested, mathematically inclined people, perhaps, which isn't necessarily a problem, but something that we should be aware of. I think something that's going to be somewhat challenging is to measure the level of participation and buy-in for people. So are they actually watching the videos? How much of the videos are they watching? This will probably become clear in the tutorials, but I guess we need to handle this in a sort of a rigorous way. And also trying to establish some kind of baseline. So we've discussed whether we should compare these to university students being taught in the sort of normal way, quantum theory. But this is also quite challenging to basically not to be comparing apples and oranges here to see if this is actually really effective, or if we're kind of stacking things in our favor. And there's probably lots of other challenges around this that we haven't thought of, which are going to come bite us in the last minute when we're writing everything up. But yeah, I'd love to hear what people think about this. And I think that's basically what I wanted to say. So thanks very much.
Well, thank you for the very interesting talk, Alex. Now we have about 30 minutes for questions. Please feel free to either raise your hand and we'll ask you to unmute yourself, or you can also write in the chat box to ask your question. There is one question. What platform will you use for teaching the kids?
In terms of IT platform, is that the question? Yeah. I don't think we've really narrowed it down so much like that. Zoom, probably, and maybe some sort of centralized place for sharing the materials, like a Slack-like thing, something like that. But also, if you have spent some time thinking about this or have suggestions, I'd be happy to hear them.
I do actually have, well, one question and a couple of comments about this one. But the first question is, you did spend quite a bit of time talking about the relations, right? Mm-hmm. And I was wondering, how are those relations are different than probability functions? Like if you have a bit, why, like, is it different than just saying this is a binary variable? If it is 0, the outcome is going to be 0, 100%. If it is 1, there's a 50% chance it's going to be 0, 50% chance it's going to be 1.
Yeah, so they're very closely related. So there is also a process theory of probabilistic processes, which would be exactly this, where I say I put in a bit and it stays 0 with, say, 25% probability, or it flips to 1 with 75% probability, something like that. Relations are a sort of a coarse graining of that. Rather than capturing probabilities, they capture possibilities. It says that basically, if I have 0, then there's some, you could read this as there's some non-zero probability that it will go to 0, and there's some non-zero probability that it'll go to 1. But I don't even know enough to say what those probabilities are. I just know that it's possible that these things could happen. But a lot of the same kind of reasoning you would do with probability theory, you also do with relations, and also talking about correlations and things being correlated or not correlated. These kinds of things all sort of translate through.
I see. So you essentially know the mapping from one state to another, but you just don't know the specific probability value.
Yeah, you just know the places where the probability is non-zero.
I see. Okay. Couple other questions in the chat. Will any small groups be taught in person?
I think all the groups will be taught online. It's simpler to do that way for various reasons, and also I guess it keeps everyone the same. We did sort of originally conceptualize this experiment during the pandemic, and that sort of pushed us in that direction. But I think just in terms of logistics, we're just going to stick with that. We didn't have any plans to teach in languages other than English yet. I mean, that would be an interesting direction to expand in. So the book is now translated in 2 other languages. So there's Chinese and Japanese versions of the big book of Picturing Quantum Processes. So it's, well, so much as pictures that I wouldn't anticipate there being a large linguistic barrier to it, but obviously we would need support to do that.
Salma also asked, how does process theory conceptualize causality, or causality is out of focus?
So process theories give you a good can give you a good handle on causality. It's some more structure that you want to put in the theory. So in particular, something that's important for talking about causality is having some kind of process which lets you throw things away. Okay, so if for instance, if you're doing like reasoning and probability theory, you know about marginalization, how you can ignore certain things. One thing that can give you a bit of a handle on causality is you can say I've got some process with say many inputs and many outputs. No, I can throw away everything but one output, and then I can see which inputs still influence that single output. And that starts to give you a handle on which things at least can influence other things. And then, you know, kind of building up from there, you can talk about whether these influences are causal influences, or you can talk about confounding and you know the kinds of things that people in this sort of causal inference area, kind of in statistical reasoning, do. You can do this in process theories.
Another question, have you exploited diagrammatic reasoning to study self-referent circular systems like autopoietic systems, if I pronounce that correctly?
In a word, I guess no. So the thing that I would say most has that characteristic. So things sort of process theory adjacent have been used. Now, there was a paper by Sampson and Abramsky some probably 7 or 8 years ago looking at diagonal arguments in category theory, which is somehow the more mathematically sophisticated, but essentially the same sort of cousin of process theory. Looking at diagonal arguments, which is a kind of a self-referential logical argument. So things like I think Gödel's incompleteness theorem and these kinds of things can be formulated as diagonal arguments in this kind of context. We haven't looked at those kinds of things really yet, but I think there's some stuff like that out there.
I do have a question about this experiment that's still in the works. So you said that the assessment is going to be through written exam. And I was wondering, especially in the context of having a baseline. So let's say that you are comparing, you know, people's learning to those like university students learning through regular classes. What would be the content of the exam like? So the reason that I'm thinking about this, if you are teaching through diagrams, let's say, and your exam content is also primarily a assessing their knowledge through diagrammatic questions, you may have your students actually perform better than, say, the university students learning through the traditional means. But in that case, it might be just because they are being taught in the same manner that they are being assessed, instead of having a general better learning overall. So I was wondering, what would that look like? What's the format?
Yeah, so we've talked about this, and I think when we were talking about comparing to university students, the idea was to write a version of the exam which is assessed in the style of a traditional quantum theory or quantum computing course. So you basically translate the exam, which we've written with pictures, into the kind of the traditional notation. And to some extent, the traditional way of framing these questions. But it's really non-trivial to really then be able to say that these are the same exam. Because also I think process theories push you to think about questions in different ways, and probably ask different kinds of questions than you would in a more traditional sort of framework. So yeah, I think doing this in a fair way is quite challenging.
Right. Is it possible to have like two versions of the exam? So maybe you can actually take half of your students, give them the diagrammatic version of the exam, and take the other half and give them the traditional exam, and do the same thing with, say, the university students. So in that case, you're essentially looking at every combination.
Oh, I see. You kind of have all four quadrants.
Yeah.
I think the problem with that is the two, let's say, off diagonal corners there. So where you're giving the high schoolers the uni notation and the uni students the picture notation.
Right.
Both of those groups would have never encountered that before, most likely. So you would expect in both of those cases they would be able to do almost nothing.
Right.
So I'm not sure if that really tells you anything that interesting.
Yeah. I haven't really thought about the notation part, but yeah, it's probably not a trivial thing. Right. And I guess I also had one maybe comment. When you are teaching this course, you mentioned that it's going to be YouTube videos and TA discussions. Are you thinking about giving the opportunity to give direct feedback or almost instant feedback to students? Like if a student, well, I guess the videos are not, they're online and they are not like real-time sessions, right?
Yeah, so the videos are not live. They're pre-recorded and
right,
and edited to be also nice to watch and kind of entertaining and so on. But yeah, I think the idea, and we haven't fixed the exact format of these kinds of discussion sessions, but the idea is that those would be more interactive. Of course, there you might have issues that certain students will interact and a few will sit in the background and so on. And
right.
Yeah, and also I saw that there was a comment that came on the chat that teaching to everyone online doesn't keep everyone the same because people have access to different amounts of quiet space and technology and so on online, which is also something that we've been thinking about and trying to sort of weigh up the options there, and also to at least have as much information as we can before we start about the kind of the circumstances of volunteers. So
right.
So
Salma also has a question. imagine that you teach quantum theory to intelligent machines by using process theory. Do you think that there's a possibility that machines could reason better and faster when this diagrammatic language is used?
I mean, so we often make this kind of argument that we humans do much better with the diagrams because we're kind of making use of something that we're good at, this kind of spatial reasoning, and this ability to see in 2 or 3 dimensions allows us to take in and work with much more information than just a big long equation, which is basically just a 1D kind of string of symbols. Haven't really thought about how that would if you thought about an AI or something thinking in this kind of way. I mean the way that knowledge is represented in the training space of a neural network or something like that is so mysterious that I don't know if it would look like anything like diagrams. One place it does help is you can use certain kinds of diagrams to represent processes more efficiently than you could in other ways, even for the purposes of writing, say, algorithms that operate on those processes. So there you can speed some things up basically by representing something as a graph rather than representing it as kind of a long string of things, which then you have to do some sort of complicated calculations on.
All right. Any other questions? Right. Doesn't seem like it. So I guess if there are no other questions, we can end it here. Thank you very much, Aleks. Again, it was a very interesting talk. And thanks everyone for joining us today.